have this problem involving three questions. We have the function f of t, where is a piecewise function. If t is strictly less than 0, the function is 0. And from t 0 and greater than 0, the function is exponentially decaying. Lambda is just a parameter on this expression, a strictly positive parameter. And here we would like to show the following, to find the following things. Question number 1, to show that this integral on the whole real line is 1 of this function, f of t. Question number 2 is to find the first moment of the function, and the third question is to find the Fourier transform of the function f of t. We want to compute this integral from minus infinity to infinity of the function. It's a piecewise function, so we split from minus infinity to 0 plus the integral from 0 to infinity. Of course, if t is below 0, the function is 0, so it's 0 dt, plus the integral from 0 to infinity lambda e to the minus lambda t dt. This term vanishes, and we just have the integral from 0 to infinity of lambda times the exponential dt. We can find easily, we can take lambda outside because it's just a constant, and the differential here is dt. It's lambda, and this we can find the integral of this function e to the minus lambda t divided by minus lambda 0 infinity. This is minus e to the minus lambda t 0 infinity. So for t going to infinity, e to the minus lambda, if t grows sufficiently large, going to infinity, the exponential is going to 0, and for t equals 0, the function is e to the power of 0 is 1. So from here we have that the integral from minus infinity to infinity of the function f of t is equal to 1. Question number 2, we need to find the first moment of the function. We call it mu1. So the first moment, we need to find the integral of t to the power of 1 f of t dt. So it's the integral from minus infinity to infinity of t times the function f of t dt. Again, I have to split the integral from minus infinity to 0 and from 0 to plus infinity. From minus infinity to 0, the function is 0, so this term vanishes, and I only end up with this term here is t times lambda e to the power of minus lambda t dt. I pull lambda outside the integral, and inside I have just t times e to the minus lambda t dt. And now I need to do integration by parts, and I choose, of course, the exponential function to do this process. is t, so this can be written as e to the minus lambda t divided by minus lambda, and this is the derivative. So if I differentiate this one, I get back to this exponential decaying function. Now I am ready to integrate by parts. So it's t e to the minus lambda t divided by minus lambda, 0 infinity, minus the integral, but I have plus 1 divided by lambda. Now the derivative hits the function, the identity function t. So I only have e to the minus lambda t dt. What do I get from here? So if you take this as t growing to infinity, you have the exponential, which decays rapidly. So this term will go to 0. So the product of t times e to the power of minus lambda t as t growing to infinity will go to 0 because the exponential goes faster towards, is decaying faster. This is one way to explain, or you can use the L'Hopital's rule and find the limit as t going to infinity. You can do whichever you like. And for t equal to 0, of course, this term vanishes. So I end up with lambda multiplying this term. And I only get the integral from 0 to infinity. So let's go to the next page. So what I get here is the following integral. From 0 to infinity, e to the minus lambda t dt. I find this integral, and this gives me 1 divided by lambda. So the first moment is 1 divided by lambda, the first moment of the function. Now I need to find the Fourier transform of the function. So I use this symbol, hat, is the Fourier transform of the function f of t. It's from minus infinity to infinity, f of t times e to the power of minus I omega t dt. Again, I split, because I have a piecewise function, I split the integral. This term vanishes, goes to 0. This term is 0 because the function is 0. So I have the integral from 0 to infinity of the function f of t times e to the minus I omega t dt. Have this integral. Of course, my function is lambda times e to the minus lambda t dt. Times the complex exponential thing. The complex exponential quantity. E to the minus I omega t dt. Now, I take a lambda outside. So I just have the integral e to the minus lambda t times e to the minus I omega t dt. E to the minus lambda plus I omega times t dt. I find this integral, divide by minus lambda plus I omega. 0, infinity. What I get from here is that I have lambda divided by lambda plus I omega. And if I multiply by the conjugate complex number, I have lambda times lambda minus I omega, and the denominator is lambda squared plus omega squared. So the Fourier transform of the function is lambda times lambda minus I omega divided by lambda squared plus omega squared. This is lambda squared divided by lambda squared plus omega squared minus I lambda omega divided by lambda squared plus omega squared. I can take the 1 divided by lambda squared plus omega squared to be the common factor, and inside I have lambda squared minus I omega lambda. So the Fourier transform depends on the symbol omega and on the parameter lambda. That's my Fourier transform. It's a complex quantity, 1 divided by lambda squared plus omega squared. And this is a complex number, lambda minus I omega lambda. Lambda is strictly positive, and omega runs from 0 to infinity.